Welcome to video 4 of chemical bonding. We are currently at this point of the lecture series. Let's take stock of our progress by revisiting the fundamental and powerful concepts. During earlier lectures, we learned that metallic, ionic, and covalent bonds are all electrostatic in nature. In this video, we will examine how intermolecular forces are similar. Specifically, we will find out more about permanent dipole-permanent dipole interactions, instantaneous dipole-induced dipole interactions, and hydrogen bonds. As an overview, intermolecular forces only exist between molecules that have simple covalent structure. This is very important. Intermolecular forces have no relevance in giant lattice structures because the particles are not discrete to begin with. These intermolecular forces are electrostatic in nature, just like the chemical bonds we learned in earlier lectures. When we speak of electrostatic, this means that the attraction is between particles that carry opposite charges. So previously, you also learned about overall polarity of molecules based on shape. Knowing this would then allow us to know the predominant type of intermolecular forces that is present between different molecules. Why do we say it's predominant? Because sometimes there may be more than one type of intermolecular force that exists. So we need to recognize which is the predominant or more obvious one. Before we move on, I just wanted to provide you a big picture of what we have covered so far. We started off with molecular formula. Knowing the molecular formula will enable us to draw the dot and cross diagrams of the molecules. From the dot and cross diagrams, we will know the distribution of electrons around the central atom. We will then know the number of bond pairs and lone pairs around the central atom. This enables us to draw the shape of the molecule using VSEPR theory. After drawing the shape of the molecule, we can deduce whether the molecule has an overall dipole moment or not. If it is polar, then it will affect the predominant type of intermolecular forces that are present. And the type of intermolecular forces present will serve to explain the physical properties like melting point, boiling point, density, so on and so forth. So essentially, we are going from a microscopic to a macroscopic level. Hopefully, this will help you appreciate chemistry better, knowing that what you cannot see has a deep impact on what you can see in the world around you. Let me reiterate that there are three types of intermolecular forces that you will study in your syllabus. When we are comparing molecules of similar MR, then the strength of intermolecular forces will follow the order as shown. There will be some checkpoints that we will go through in subsequent lectures that illustrate this point. The first intermolecular force that we will be introduced to is permanent dipole-permanent dipole, in short PD-PD interactions. These interactions are weak electrostatic forces of attraction that exist between polar molecules. It involves the oppositely charged regions of molecules that have differing electron density. Let's assume that this diagram depicts HCl molecules. Every HCl molecule has an asymmetric distribution of electron density as shown by the electron cloud here. I trust that you remember this is due to the difference in electronegativities between H and Cl atoms. So what is between the molecules is PD-PD interactions. At this point, I want to gently remind you that within each HCl molecule, the strong covalent bond still exists. So please do not confuse the covalent bond with PD-PD interactions. There is only one factor that affects the strength of PD-PD interactions, which is the magnitude of net dipole moment. During the March holidays, we learned what is net dipole moment through the SLS lesson package. So if the net dipole moment of the molecule is larger in magnitude, then naturally the molecule is more polar, with a more pronounced delta plus and delta minus on the ends of the molecule. This results in stronger PD-PD interactions. The second intermolecular force of attraction is known as instantaneous dipole-induced dipole, in short ID-ID interactions. There are weak electrostatic forces of attraction that exist between non-polar molecules. Something worth reading more in detail is how ID-ID interactions form. Usually, the electron cloud of a non-polar I2 molecule exists like a perfect oval, showing the equal distribution of electrons. But electrons are continually moving in their orbitals, so at a particular point in time, there will be an asymmetric distribution of the electron cloud. There will be a region of the molecule with slightly higher electron density than another region, which gives rise to an instantaneous dipole. The keyword here is instantaneous, for a short moment in time. Once again, I'm showing you this diagram to highlight the difference between ID-ID interactions and the strong covalent bond within the molecule. So once an instantaneous dipole forms, it is going to induce another dipole in a neighboring non-polar molecule. Therefore, these two molecules become attracted to each other. To illustrate my point, this diagram shows how the molecule on the left has an instantaneous dipole, which then induces a dipole on a neighboring molecule. So the electrostatic force between the molecules is known as ID-ID interactions. At this juncture, I think it will be good for me to introduce you to this word polarize. When an electron cloud is being distorted, we term this as polarization, or the electron cloud is being polarized. As we mentioned, the electrons are continuously moving, which is why the asymmetric distribution of electron cloud is lost very quickly. Just as the instantaneous dipole is lost, almost immediately another instantaneous dipole will form. So this goes on and on, such that the net effect of all the interactions will hold the nonpolar molecules together. So this is another diagram to represent the formation of ID-ID interactions. There is only one factor that affects the strength of ID-ID interactions, which is the number of electrons. When there is a larger number of electrons in the molecule, the electron cloud is more diffused and less attracted to the nucleus. This causes it to become more polarizable or easily distorted by another molecule. And this results in a larger dipole moment and hence stronger ID-ID interactions. Let's move on to something else that is related, which is the extensiveness of ID-ID interactions. Please be very careful. The terms strength and extensiveness do not refer to the same thing. So extensiveness of ID-ID interactions is affected by surface area of the molecule. If you compare a straight chain molecule with a branch molecule, obviously the straight chain molecule has larger surface area. This allows more sites for ID-ID interactions to form, and we refer to this as more extensive. There is one thing that I should highlight though. The term extensiveness is only applicable to isomers, which are molecules with the same MR and therefore the same number of electrons. Why is that so? If the molecules have the same number of electrons, then the strength of ID-ID interactions is kept the same. So if you need to bring up another factor to explain the difference in, say, boiling point, you can use extensiveness to compare the ID-ID interactions. We will see such an example in checkpoint 16, not to worry. So at this point in time, I would like to quickly clarify a misconception. This is the context provided. We encountered this molecule CHCl3 in an earlier lecture. Due to its shape, it is a polar molecule. So is it true to say that since the molecule is polar, there should be no ID-ID interactions? The answer is false. Why is that so? Because ID-ID interactions do not just exist between nonpolar molecules, they exist in all elements and compounds with simple covalent structure. It just so happens that ID-ID interactions are usually more significant for non-polar molecules and atoms of noble gases. Because for non-polar molecules and noble gases, they only have ID-ID interactions as intermolecular forces. Whereas for polar molecules, they can have PD-PD interactions or hydrogen bonds. but we should not neglect the fact that they have ID-ID interactions. The key is to determine which one is more predominant. So like what this cartoon shows, as long as you have electrons, ID-ID interactions can occur between you and your neighbors. We should also be aware that there is a chance that ID-ID interactions can be stronger than PD-PD interactions, provided that the number of electrons is high enough. For example, if we compare butane and propanone, I trust that you know by now that butane is a non-polar molecule because it only consists of C and H atoms. On the other hand, propanone is polar as it has an overall dipole moment caused by the electronegative O atom. So we would expect only ID-ID interactions to exist between butane molecules, while both ID-ID and PD-PD interactions would exist between propanone molecules. Comparing the MR of these two molecules, both are 58. This gives rise to a similar number of electrons in both molecules, so we can take the strength of ID-ID interactions in both molecules to be the same. Then what is the factor that contributes to the higher boiling point of propanone? It has to be the PD-PD interactions. So this is a straightforward case. However, if we were to look at hexane, which is non-polar, we see that its boiling point is much higher at 68 degrees Celsius compared to 56 degrees Celsius. Given that the MR of hexane is 86, we know that only ID-ID interactions exist between hexane molecules. Then why is the boiling point of hexane higher than that of propanone? The only way to explain is that the strength of ID-ID interactions between hexane molecules is stronger than the PD-PD interactions between propanone molecules. Let us move on to hydrogen bonds, which is the final intermolecular force of attraction we are going to learn. Hydrogen bonds, by definition, are weak electrostatic forces of attraction that exist between the protonic hydrogen of one molecule and a lone pair on a highly electronegative atom of another molecule. This is quite a mouthful of words, so let's use a diagram to better illustrate this. There are three water molecules drawn. If you recall VSCPR theory, you would know that the water molecule is band-shaped as there are two bond pairs and two lone pairs surrounding the central oxygen atom. In each water molecule, the OH bond is polar, with O being the more electronegative element getting the delta minus charge, and H will be delta plus. When two water molecules are brought close together, the electron-poor H will experience an electrostatic attraction towards the lone pair on the O of a neighboring molecule. So this is the hydrogen bond formed. So take note that when you are drawing a diagram to represent hydrogen bonds, there are a few things that you must include, known as marking points. Number 1, the lone pair of electrons. Number 2, partial charges on O and H. Number 3, a dotted line to show the hydrogen bond. And number 4, label the hydrogen bond. For hydrogen bonds to be present, there are some special terms and conditions. First, the molecules must definitely have at least one H atom directly bonded. The word directly is very important, so you must really check the molecule to ensure that the H atom is directly bonded to a N, O, or F atom. Second, the neighboring molecule that it is hydrogen bonded to must have at least one lone pair of electrons on the N, O, or F atom. So you see this NOF is a unique set of elements that are relevant to hydrogen bonds. Therefore, you will need to commit this to memory. There is only one factor that affects the strength of hydrogen bonds, which is simply the polarity of the HX bond. In an earlier lecture, we learned about how the polarity of a covalent bond is dependent on the difference in electronegativities of the elements involved. So to illustrate, the HF bond has the greatest difference in electronegativity out of the three bonds listed. So naturally, it is going to be the most polar, followed by the OH bond and then the NH bond. So when the bond itself is more polar, it will result in a stronger hydrogen bond. Next, we will examine some consequences of hydrogen bonds. Why is the dimerization of carboxylic acids relevant? If you look at the diagram very carefully, you would have noticed two ethanoic acid molecules drawn, and they are hydrogen bonded to each other. This phenomenon usually occurs in liquid and solid states. However, in aqueous state, when water molecules are in large excess, carboxylic acid molecules will preferentially form hydrogen bonds with water molecules. So in other words, this dimerization, which results in a doubling of the MR, is going to be more relevant in the liquid and solid states. At this point, I just wanted to jog your memory. Is this the first time we have seen dimerization in chemical bonding? No. We have also learned about the dimerization of AlCl3 on page 18 of your notes. The subtle difference is that AlCl3 dimerizes using dative bonds. Here, the dimerization of carboxylic acids happens using hydrogen bonds. So please be aware of the different contexts. Moving on to the final part, which is the famous example of water and ice, we should all know that ice floats. Why is this so? Because if you examine the molecular structure of ice, you will notice that every water molecule forms hydrogen bonds with four other water molecules. As a result of this, each oxygen atom is surrounded tetrahedrally by four hydrogen atoms, two by covalent bonds and two by hydrogen bonds. So this has to do with the orientation of molecules. So when this happens, ice will adopt an open and crystalline structure. The regular arrangement causes water molecules to be more widely spaced apart. This is the microscopic property of ice. The macroscopic implication is that water expands when it freezes, resulting in a lower density of ice as compared to liquid water. So this is why when you have a glass of Coke and you put ice into it, the ice floats. No matter how hard you try to press the ice to the bottom, it will still float up. This is due to its lower density. And why lower density? It's because water molecules in ice are more widely spaced apart. So for a fixed volume, you have a lower mass of water molecules. We have come to the end of video 4. I hope you have gained a better appreciation of what are PD-PD interactions, ID-ID interactions, and hydrogen bonds.